Okay, YouTube, in this video we're going to continue our discussion of transformations of graphs, and specifically we're going to be looking at reflections as well as stretching and shrinking. So let's go ahead and start by looking at reflection transformations and how that kind of shows up with the function notation here. So we say let's graph p of x equals negative the absolute value of x and its parent function and describe the transformation, okay? So you'll notice that I've already made our doubly augmented table here where we have x and f of x, where f of x is the parent function, okay? We know that this is our parent absolute value function that looks like a v. And then we have our transform parent function where you'll notice that all I'm really doing is taking the original outputs and we're making them negative, okay? So let's go ahead and consider at least the parent function here. If we said, let's plug in negative 2 into the absolute value of x here, we say the absolute value of negative 2, f of negative 2 is going to be a positive 2. Whereas if we plug in negative 1, we get a positive 1. Absolute value of 0 is 0. Absolute value of 1 is 1, and the absolute value of 2 is 2. But essentially, remember, absolute value is going to take these values in here and revert them to being positive. Now, the thing with p of x here is if we were to find p of, say, negative 2, really what we're getting is this. It is the negative absolute value of negative 2. And evaluating the absolute value first, we're going to notice here that that's a positive 2. The absolute value of negative 2 is a positive 2, but we had a negative out front. So it actually turns out to be a negative 2. And likewise with this 1 here, basically what we're going to be doing is taking all these original outputs, these absolute values of x, and making them negative. So if this was a 2, this is a negative 2. If this is a 1, it's just going to make this a negative 1. Negative 0, well, 0 is a neutral number. We have 1, make that negative, we get negative 1, and then negative 2 here. So let's go ahead and graph these out, starting with the parent function. Now our parent function, recall that the parent function of the absolute value graph starts at the origin, kind of goes up 1, right 1, up 1, right 1, up 1, right 1 to the right, but also does so to the left, okay? So we have this graph that looks like a V. That is the basic characteristic of our absolute value parent function. Now, when we consider, though, putting a negative in front of this right here, what really happens is when we graph these, we get negative 2 comma negative 2, we left 2 down 2, we get negative 1 mapped onto negative 1, 0 maps onto 0, 1 maps onto negative 1, and then we have 2 mapping onto negative 2. Essentially, if we'd say, well, then describe what changed about this graph. What kind of a transformation did we see occur here? We didn't change the shape of this graph, and we didn't translate it or shift it, but basically we have a reflection transformation. Reflection. So it is fair to say that when you have a function f of x, if you were to go through and make all of the y values, the original y values on your parent function negative, it's going to reflect it over the x-axis here. If you make all the y values negative, it's going to reflect it over the x-axis. So we say a reflection is a transformation that flips a graph over a line called the line of reflection. Okay. So now let's consider graphing and describing stretches and shrinks. When we look at these functions down here, we're also going to graph the function and its parent function and describe the transformation. And you'll notice that I did set up some doubly augmented tables here. We have g of x is 2 times x squared. And we can put in any input values we want. I'm going to go ahead and use a pretty solid battery here from negative 2 to 2 going by increments of whole numbers. But basically, the parent function here, if we were to plug in all these values, we know what the parent function of a squared thing looks like, a quadratic function. But basically, it's a U-shaped thing that starts at 0, 0. So let's go ahead and fill out its values here. Basically, if we were to plug in now f of 0, 0 squared would be 0. 1 squared would be 1. 2 squared would be 4. And then likewise going the other way, if we said negative 1 squared, we get a positive 1. And negative 2 squared, we get a positive 4. So here's our parent function of a quadratic type. And we get this U-shaped graph. Okay. So now the real question becomes, what if we were to put a 2 in front of this here? Basically, what's going to happen is we're going to take all these original x squared outputs and we're going to double them. So we would get 8, 2, 0, 2, and 8. And going through and graphing these, I'm going to graph these in purple here. We get 0, 0 still, but we get 1, comma 2. We get 2, comma 8. So that's going to be way up here. Then we have negative 1, comma 2, and negative 2, comma 8. That's this guy right here. But we still get a U-shaped thing. It's just that if I said describe the transformation that we see here, what I notice is all of the y values stretched a little bit further from the x-axis than these ones right here. As a matter of fact, they're twice as far from the x-axis. So we see that this is a vertical, what we're going to call stretch. I'm going to say it's a vertical stretch by a factor of 2. Okay? So now let's consider h of x here. We have some absolute value function, or some function in the absolute value family, something that looks like a v. Okay, so let's go ahead and replace these blanks with our x values that we choose to plug in, and start with our parent function. Now our parent function, we can just adopt these values that we saw up top. Remember, when you take the absolute value of a number, what's going to happen is it just becomes non-negative. It becomes positive or 0. So in this case, we still have our parent function, that is this function that looks like a v, starts at the origin, goes up one, right one, up one, right one, up one, right one, all the way to the right, and then it does this to the left also. So here's our absolute value parent function. So a graph of f of x. Should label that. Now the question becomes, well, what happens if I take all those original y values and I take them times a half? Well, what's going to happen is they're going to become half the size. So half of 2 is 1. Half of 1 is just a half. Half of 0 is 0 halves, or 0. And we get a half here as well. We get 1 here. So going through and graphing these, we say, well, we have 0, 0, but we get 1 comma a half, 2 comma 1, negative 1 comma a half, negative 2 comma 1. And you'll notice that we still get a V-like graph. We get a V-shaped graph. But if we said, now, what happened to all the original y values? You'll notice that they are half of the distance between the original y value and the x-axis. So what we say is, this has become a vertical shrink. And if I said by what factor? By a factor of a half. So it would be easy to kind of come to a conclusion that if you were to take all the original y values and multiply them by 1, nothing would change. But to multiply them by a number bigger than 1 is going to cause a vertical stretch. So a general conclusion is essentially this: vertical stretch occurs when our parent function, we'll say g of x, which is our new function, is equal to our parent function, where we take a times f of x, and I'm going to say a is greater than 1. Okay, this is going to be stretch. In other words, we're taking our original function and multiplying all the original y values by this number a, where a is bigger than 1. And if we want to refer to a shrink, we'll write it here, shrink, then we say that our new function g of x, or h of x in this case, but say g of x is equal to a times the original parent function, where we say a, it's bigger than 0, but it's less than 1. In other words, it's a proper fraction. So if you took something times like 2/3, of course it's going to be 2/3 the size. So after drawing that conclusion, I really quickly want to visualize what would this look like. You can honestly visualize this kind of this way. If we had an original parent function, say here in blue, we can imagine stretches being the points pulling away from the axis here, because we're multiplying them by a factor bigger than 1. Whereas if we wanted to visualize vertical shrink, imagine pushing the points toward the x-axis, because we are multiplying them by a proper fraction. Okay. So the very last thing I want to do in this video is essentially use a graphing calculator for this one. But what I want to do is graph this absolute value function in a graphing calculator, and also its parent function, and describe what kind of transformations we're seeing using terms like translation, reflection, and stretch. Let's get our graphing calculators on here. And we're going to put this function in here for y equals. So let's go into y equals. We'll clear this out. And we say -2. Now it's important you use this key here instead of the subtract key for negative. But we say -2. And to find absolute value. Now, one way to do this is to go to this little word down here that says catalog. So it means you're going to have to hit your yellow key or your second key first. But if we go to your catalog, you'll notice the very first function here is ABS, and that stands for absolute value. I'm going to hit enter. But it's -2 times the absolute value of, well, we have x minus 2. We just need to end that parenthesis, and this acts like absolute value of x minus 2. And we'll subtract 3 off of this. And we also want to graph the parent function. So I'll also hit enter, and we'll go to y2. And this time we're going to graph the absolute value of, so we'll go back to our catalog here, ABS, absolute value of x, our basic parent function. So let's look at the transformations we see take place. Instantly, I notice that this opens downward. So we could say it was reflected. If this is our original parent function, it's reflected over the x-axis. I also notice that this one is a little bit more vertically stretched. Okay, it's a little bit skinnier. And last but not least, I noticed that it was shifted right and down. And I would say that if we could zoom in here, it's kind of easier to tell, but we'd say it was shifted right 2 and down 3. So as far as our transformations are concerned, we have an x-axis reflection. Okay. That was one transformation. We have a vertical stretch, vertical stretch. And then we have translations, right 2, and down 3. Our goal in the future will be to indicate these things by looking at the function. For instance, here I knew this was vertically stretched by a factor of 2. Since it's negative, we're going to have a reflection. And this is going to shift it right 2 and down 3. Cheers.